I'm going to be presenting this paper, A General Theory of Sample Complexity for Multi-Item Profit Maximization. And this is joint work with Nina Balcan and Tuomas Sandholm. So setting prices and designing auctions is an incredibly challenging problem with tremendous real-world impact. So for example, Amazon has to choose how to price every single item it sells. The government has to design spectrum reallocation auctions. And of course, big internet companies have to design ad auctions, which can generate huge amounts of revenue. And a priori, it's not always clear what prices we should set or what type of auction we should use. So in this work, we're going to talk about how can we use machine learning to design mechanisms with high expected profit. Okay, so why should machine learning be a good tool for this problem? To answer this question, I'm going to remind you of a standard assumption made for decades in economics, which says that a buyer's value for a set of goods is defined by a probability distribution over all the possible values that buyer might have for those goods. And crucially, we often assume that the mechanism designer knows this distribution a priori. So for example, this is the assumption in Meyerson's optimal auction. And this question has already come up a couple times in this session, a pretty natural question. Where would this information come from? I don't know this distribution governing my values in my head. Why should a mechanism designer know this distribution? So in this work, we're going to relax this common assumption that the mechanism designer knows this distribution. Instead, we're going to assume there's an unknown distribution over buyer's values. The mechanism designer gets a set of samples from this distribution, which he uses to learn a set of prices, or maybe an auction format. And ideally, this set of prices should garner high expected profit on this underlying unknown distribution. Okay, so I just want to go over what exactly is this learning-based mechanism design procedure. So first thing, the mechanism designer is going to fix some class of mechanisms to optimize over. So for example, this could be the class of second price auctions with reserves. The mechanism designer wants to tune this reserve. Next, he's going to look at the samples, and he's going to find a mechanism from his class with high average profit over this set of samples. And then he'll field that mechanism. And so the natural question here is, will that mechanism that we field have high expected profit on that unknown distribution? And this high-level question motivates this paper's central question, which is specifically, will average profit on the set of samples nearly match expected profit on this unknown distribution for any mechanism in this class? If the answer to this question is yes, then we know that a mechanism that has nearly optimal profit on average over the samples is also going to have nearly optimal expected profit on this unknown distribution. So we'd really like to answer this central question. Okay. And of course, the answer to this question depends on the mechanism class that you're optimizing over. So our contribution is a general theory applicable to any mechanism class exhibiting a key structural property, which I'm going to talk about on the next slide. This theorem bounds the difference between expected profit and average profit on the samples for any mechanism in this class. So it answers this central question. And what makes this theorem interesting is that this structural property is shared by a diverse array of mechanism classes. Okay, so what is this structural property? It's simple to state. It says that for any fixed set of buyer values, profit is a piecewise linear function of the mechanism's parameters. That's a high-level version of this structural property. And mechanism parameters, I'm going to give you some examples later on, but for now you can basically think of these as prices. It definitely applies beyond just pricing schemes, but you can think of these as prices for now. And I'm going to give some examples of these, this structural property in action, but before that I actually just want to point out a small fact about this structural property that's actually a little bit subtle, and which is what allows us to actually prove these guarantees that we're going to give. So let me just remind you what we want to prove. We want to prove that for any mechanism parameters P, so for any mechanism in this parameterized class, average profit over the samples is close to its expected profit. So here S is a set of samples, and so we're looking at average profit over the set of samples of this mechanism parameterized by P. Okay, this is what we want to prove. So in particular, this function class that we care about is this class of functions that measures, given a set of buyer values, what is the profit of the mechanism parameterized by P on that set of buyer values. So this is a function class we want to prove these convergence bounds about. And the way we do this is actually by looking at a dual class. So the dual class fixes a set of buyer values and looks at what is profit as a function of the parameters. And so this structural property, which says that for any fixed set of bids, profit is a piecewise linear function of the mechanism's class's parameters, that's a property of this dual class of functions. And by exploiting this dual class of function structure, we're able to prove facts about the primal class. We're able to prove uniform convergence bounds for this class we actually care about. So it's really looking at this dual class of functions that's the key. Okay, so now I'm going to give you some examples of this structural property. So the first is a very familiar mechanism class, the second price auctions with reserves. And here the reserve is the mechanism's parameter. And we all know this auction. The auctioneer sets a reserve price R. The highest bidder wins if his bid is above R, and he pays the maximum of the second highest bid in the reserve. Okay, so the reserve is our parameter, so we can think about the reserve here on the x-axis, profit on the y-axis. Now we want to say for any fixed set of bids, profit is piecewise linear function. So let's just say the second highest bid falls here, the highest bid falls here. Let's see that this function is actually piecewise linear. So if the reserve is smaller than the second highest bid, the highest bidder is going to win, and he's going to pay the second highest bid. So profit is just constant here. If the reserve price is between the second highest bid and the highest bidder is going to win. He's going to pay the reserve price. So this function here is just f of x equals x. And of course, if the reserve is greater than the highest bid, no one's going to win, no one's going to pay anything, so profit is 0. So indeed, profit is a piecewise linear function of this mechanism class's parameter. So now let's move on to a slightly more complicated class. Posted price mechanisms, still pretty simple. There's just a price per item. So these, again, are the mechanism class's parameters. There's going to be a fixed but arbitrary ordering over the buyers. The first buyer is going to come buy the bundle of goods that maximizes his utility, so that's his value minus price. Second buyer is going to come in, buy the bundle of remaining goods, maximizing his utility, and so on. So now we've got a multidimensional parameter space. So we've got the parameters here. Let's say there are just 2 items for sale, a coffee and a muffin. We've got the parameters on the xy axis, profit on the z axis. We want to show that this function is piecewise linear. And let's think of a really, really simple case, just for an illustration, where there's just a single buyer. Values for the coffee is 1, value for the muffin is 2, value for the bundle is 2.5. So we can reason about in what regions of the parameter space the buyers will prefer which bundles of items. So for example, the buyer is going to prefer the coffee over the muffin if his utility for the coffee is greater than his utility for the muffin. Or in other words, 1 minus the price of the coffee is greater than 2 minus the price of the muffin. So I've just substituted his values in there. And this defines a hyperplane in R2, where on this side of the hyperplane, the buyer is going to prefer the muffin. This side, he's going to prefer the coffee over the muffin. And we can similarly look at all pairwise comparisons here and come up with a partition of the parameter space, where in this region, the buyer is always going to most prefer the bundle of the coffee and the muffin. In this, if the prices are in this range, he's always going to want the muffin, this range, the coffee, and in this range of the prices, he's never going to want to buy anything. And okay, so for any fixed set of bids here, for example, the ones we use to make this picture, profit is going to be a piecewise linear function of these two parameters, because in this region, we know the buyer is going to want the coffee and the muffin. So the profit is going to be the price of the coffee plus the price of the muffin. So it's just a piecewise linear function of these two parameters. And I plotted it, so you can see it's piecewise linear. And of course, this structural property you can probably imagine is also going to hold when we have multiple buyers, but I'm not going to go through that here just because of time. And we also prove that this structure is exhibited by a ton of other mechanism classes. So these are like randomized mechanisms, nonlinear pricing mechanisms, affine maximizers, virtual valuation combinatorial auctions, mixed bundling auctions, and so on. Okay, so let me now remind you, why do we care about this structural property? We wanted to prove this uniform convergence theorem that told us how close average profit on the set of samples is to expected profit on the distribution. So now I'm going to relate this structural property to this uniform convergence bound. So this is our main theorem. So like I've been saying, suppose that we have this mechanism class parameterized by vectors in some d-dimensional space. So for example, again, you can think of these as prices, but it's more general than that. And moreover, suppose that for any buyer values v, so this is a vector of buyer values, there's a set of at most t hyperplanes splitting the parameter space into regions where in any cell of this partition, profit is linear. So this is what we saw here. We saw that we're looking at this d-dimensional parameter space, and there are 5 hyperplanes splitting this parameter space into regions, where in any one region, profit is linear. Okay, so if both of these conditions hold, then we have this guarantee. For any delta with probability 1 minus delta over the draw of a set of samples from this distribution, for all mechanisms in this class satisfying these two properties, the average profit over the set of samples minus the expected profit on the distribution is bounded by this function. And this function depends on U, the maximum profit of any mechanism in this class over the support of the value distribution, N, which is the number of samples, D, the dimension of this parameter space, T, the number of hyperplanes creating this partition, and delta, which is our failure probability. So D and T and delta don't depend on the number of samples at all, so we could send the number of samples as large as we want, and this difference is going to go to 0. And just how fast this difference goes to 0 depends on the complexity of the mechanism class, which is kind of encoded by D and T. Okay, and I want to talk a little bit more about some of these applications of this main theorem. So using this main theorem, we're able to match or improve over many of the best known guarantees for classes that have been previously studied in the mechanism design literature. So these include posted price mechanisms, affine maximizer auctions, second price auctions with reserves. And we also look at mechanism classes that were not previously studied in the sample-based mechanism design literature, such as randomized mechanisms and multi-part tariffs, other nonlinear pricing mechanisms. And just to wrap up, I want to talk about a few more results that are in this paper. So the first of which is data-dependent guarantees. So my main theorem was for worst-case distributions. It held no matter how terrible the distribution over buyers' values is. And in this paper, we also get better guarantees when the distribution over Bayer's values is well-behaved, and certain definitions of well-behaved. And we also investigate kind of a fundamental trade-off in sample-based mechanism design, which says that if you're trying to optimize over a complex class, there's probably going to be a mechanism in that complex class that gets really good profit, roughly speaking. However, you're going to need many samples in order to ensure that for any mechanism in that complex class, average profit is close to expected profit. So there's this trade-off. If you look at a simpler class, then there might not be as good a mechanism in that class, but you're going to need very few samples to ensure this, that performance on the samples generalizes to the distribution. So we provide techniques for optimizing this trade-off. So thank you.
Questions?
Thank you. So about the bound you give on the deviation between the sample average and the expected profit, should I better think of this as worst case upper bound, or like in all cases it's going to be order of that?
Oh yeah, you can think of it. So the question was for that generalization guarantee from our main theorem, which bounds the difference between expected profit and empirical profit, can I think of that as a worst case bound, or will it maybe for some distributions I'll get better bounds, right? Yeah, so definitely for some distributions you're going to get better bounds. And a really interesting future question, which we do look at a little bit in this paper, but I think there are tons more to explore here, is how to get better data-dependent bounds for nice distributions over Bayer values.
Other questions? Just wondering, do you have any examples of sort of mechanisms where profit is not piecewise linear?
I guess not off the top of my head, but I'm sure they exist. And yeah, I'm sure they exist, yeah.